And Rachel, is this too much in the way?
Oh, no, okay.
Okay.
We should try that right here.
All right, any questions? Okay. See, we finished the ski problem, I believe. And to the point of the skier, we did the skier running into the spring and then going back up to the top of the hill. Okay. All right, so we started out with trying to come up with a way of sort of describing motion. We came up with the acceleration, velocity, position, displacement, key terms like that. Then we got into the relationship between force and acceleration using Newton's second law. And then we expanded that into this idea of also looking at the way things move in terms of energy. And so now, momentum. I am going to go through a derivation right now, just like I did with energy. I'm not doing this so that you can regurgitate it later. I'm doing this just so that you see that this stuff comes from somewhere. It's not that, although some students would be satisfied with, hey, here's the formula, I'm not satisfied with that because this stuff does not appear out of a vacuum. So if we go back to that collision scenario, I had object A and object B hitting each other and then bouncing apart. And I said that there were three things in common. One is that they exert the same magnitude of force on each other. That's Newton's third law. So the force on A from B is equal to the negative of the force on B from A. That the displacement while they're touching each other is the same, and that led to this idea of work and energy. And the third thing was that the time they touch each other is the same, and so that's what we'll exploit this time. So the force on A from B times the amount of time that they're touching is equal to the negative force on B from A times the amount of time that these two objects touch. Or we can make it more generalized, they don't actually have to touch while they interact. So if I take an object and I drop it, as it falls to the earth, the object's falling towards the earth is coming up towards it. Not much, but some. And so while the interaction is going on, this still holds true. All right, Newton's second law. What does F equal? That's what I'm going for. So this is the mass of A times the acceleration of A times time. It's the negative mass of B times the acceleration of B times time. And what is acceleration times time? All right, what is acceleration?
The change of velocity over the time.
Okay, so this is the change in velocity over the change in time. So if I treat this like two fractions equal to each other, so what's acceleration times time? Or change in time?
Velocity. Change in velocity.
Yes. The fact that it's change is important. And so acceleration times time here is just the change in velocity. So this is the mass of A times the change in velocity of A equals the negative mass of B times the change in velocity of B. And when I say when we talk about change in velocity, what am I subtracting from what? What's change in anything? What am I doing?
Final minus initial.
Yes. Seem to be having issues.
No, it fits. My nose is just rough.
Oh, have a free mask. Once I put it on the table, I thought, well, it's yours. Which makes me wonder about those. All right, so it's final minus initial, so this is the mass of A times the final velocity of A minus the initial velocity of A equals the negative mass of B times the final velocity of B minus the initial velocity of B. One more really tedious line and then we'll simplify. So I'm going to go ahead and distribute. So I have the mass of A times the final velocity of A minus the mass of A times the initial velocity of A equals the negative mass of B times the final velocity of B plus the mass of B times the initial velocity of B. And then I make sure, or at least do a quick check and make sure that my subscripts are looking good. I think they are. If you notice, well, it's true whether you notice it or not, but MV pops up a whole bunch there. So when the same thing pops up again and again, what physicists do is they look at it and go, hey, come on, let's come up with a letter to represent that. And so they looked deep into its soul and decided the letter P is probably the best thing to use for that. So P is equal to MV. And so this just becomes P final of A minus P initial of A is equal to negative P final of B plus P initial of B. These are vectors. There does need to be the vector symbol over the P. And then, of course, they looked at that and said, hey, well, let's get all the initials things together and all the finals together. So we got the final here and the final there, so let's bring that, the PFB over to the left and the PIA over to the right. And the way you do that, the terms is you add or subtract whatever the opposite is. So I have P final A plus P final B equals P initial A plus P initial B. At which point the physicist's heart gets all a twitter because we have this total final right here is equal to the total initial. This is a conservation law. When the sum of all the final terms is equal to the sum of all the initial terms. This P, of course, is momentum. I did see once why they chose the letter P, and I forget what it is. I've seen several videos out there where people go, hey, you know why they choose the letter P? I don't know. That very unsatisfying, but it is sometimes one of those mysteries in physics about why they choose a particular letter. If in doubt, it's from the Greek or the Latin. And I believe possibly Rene Descartes is to blame. So, the power of this because we have this new conservation law. The power is the fact that we really don't care what happens during the interaction, just kind of like we were doing with energy. If I know what happens is going on beforehand, I can predict what's going to happen afterwards. Now, we have dealt a lot with constant acceleration. This officially is the formula for average acceleration. And if acceleration is constant, then the average is equal to the value of whatever it is. But it turns out if you do this with calculus, you get to the exact same place. Right. So before we do an example here, a couple more vocabulary words. There's force times time on the left-hand side. If we work our way down, I don't change anything from sides until I get to here. So everything on the left-hand side of the equal sign they're all equal to each other. So this down here where I have this final minus initial, this is just change in momentum here. So I can write that the force times the change in time is equal to the change in momentum. This has a special name, and this is what I will consider my most obscure clue. It used to be the G2 Kombucha, but I actually had somebody who knew that one. This one comes from a television commercial in the 70s. You can find it on YouTube. When someone suddenly buys you flowers, that is called not up on your 70s TV commercials. What about if we ignore the commercial part? If someone suddenly buys you flowers, what is that called? Wow. There's no word for it? You're speechless? Usually class says that's nice, but I guess not for this group. The commercial was for a perfume called Impulse. This is impulse. If I apply an impulse to an object, it will change the momentum. Just like if I do non-conservative work to an object, I will change its total energy. If I do conservative work to an object, I will transfer energy from one form to another. If I do impulse on an object, I will change its momentum. There are a couple of questions in Hewitt where he talks about impulse and whether you find impulse by force times time or find impulse by change momentum depends upon what's given in the problem. If you're given enough information to find it this way, do it that way. If you're given that information, do it that way. A side note, if those are equal to each other, then if I divide by time, I get F is equal to the change in momentum over the change in time. And what is the formula for momentum?
MV.
Yes, just like it's written over there. So this is the change in mv over the change in time. Now, if the mass stays constant, then this becomes mass times change in velocity over change in time. So this, again, this is if mass is constant. Which is just mass times acceleration. That's Newton's second law. However, if mass is not constant, Newton's second law of F equals ma doesn't quite work particularly well if the mass does not stay constant. For example, a rocket problem. Because when a rocket is launched, it is shooting burned fuel out the back. It is losing mass as it goes. And so F equals ma becomes a lot trickier. So this right here is really the more generalized formula of Newton's second law. Okay. Questions up to here before we actually do some numbers? Let's do some numbers. Those numbers I want to use, yes they are. What is the momentum of this object?
Newtons.
Nope. I'm good with the 15, not with the units. All right, so how'd you get 15?
Multiply 5 times 3.
All right, so it's the mass, so the momentum. And put a little 5 down here to indicate it's the momentum of the 5 kilogram object. Is the mass, 5 kilograms, times, wait, that's the speed. What's the velocity? What's the difference between speed and velocity?
Direction.
Direction.
All right, so how are we going to indicate direction here?
Direction for the east.
East?
Yeah. That's it.
Okay. So east. Is there a faster way of doing it instead of writing the word east out? Because
Arrow.
okay, we could do an arrow. Is there a faster way than that? Could go that route as well. And there's actually another choice, the one that I was originally thinking of, but all the other things that people have said are correct. It's a one-dimensional problem.
Positive.
Yeah, we could just say, well, let's say take to the right positive, and therefore we can get away with it. It's going to turn, as we expand this problem, this is actually going to be the simplest way of doing it, because we're going to add in something going the other direction in just a moment. All right, so I'm indicating to the right is positive, and so there we go. So 15, and now we back to the units. What are the units of momentum? And the hint is there is not a single word unit to cover it.
Kilograms, meters per second?
There you go. Now, if you want to go newtons, also, try that again. You could also do 15 Newton seconds, multiplying them. If you think back over here, if these are equal, the units have to be equal. I have momentum on one side, and over here I have force times time, so a Newton second is a legitimate unit for Newton, or for momentum. I do not know why they don't have a single word for it. So, not that we have to do it much, but there is a shorthand that you could take. You can make up your own unit if you want to. So what I'm gonna do is I'm gonna make up my own unit over here. If you're gonna make up your own unit, you don't have to use the one I picked, but please make sure you're not picking the unit that's already being used. Don't use capital N to represent the unit of momentum, because capital N's already been taken. The 3 lines indicate this is, I'm defining it. This is 1 kilogram meter per second. D for Descartes, because he was doing some of the early work on this. So while that's on the board, this is also legitimate. Now, because I've made this unit up, this is only legitimate as long as I've defined it. So if I'm erasing the board, and I start over here and I erase this, that is now wrong. It's not universally accepted. Matter of fact, it's not, anyone, if you did this with anyone outside of anyone who's had me before, they'll look at you strangely. If they have had me before, they're gonna probably go, oh yeah, he did do that, didn't he? So let's make it legitimate again by putting this back up. 1 kilogram per second. All right. Keep the same convention to the right being positive. And although the numbers are not really critical here, I think I picked these numbers for a reason, so I'm going to try to maintain what I have in my notes. 4 kilograms going to the left at 6 meters per second. So the momentum of the 4 kilogram object is what?
minus 24.
Minus 24? So far so good. Are you stopping there?
Newton F.
You just refuse to use my thing, don't you?
Yeah.
That's fine. All right. So we have negative 24 Newton seconds, or negative 24 kilogram meters per second, or negative 24 Descartes. So, any questions about where this 24 comes from, or where the negative 24 comes from? Okay. You about to ask a question? All right. So now what I want to know is, these two things are going to hit each other, but before they hit each other, what is my total momentum? So my initial total momentum. Not a complex problem. Might be a complex concept, but it's not a complex math problem. The total initial momentum. Anyone want to take a shot at it?
Negative 19?
How'd you get 19?
Or added the 2?
Okay, the process is right, small error, negative 9.
So, because there's only, never mind.
Which units do you want to
I
go with?
added it wrong. Good question.
If-
Oh,
Just pick one.
D.
D? All right. Somebody's going. Now, sometimes I do that, especially with the mask on. You can't catch some of the facial expression. I don't have any emotion set up in it, it's just something I do. All right, so that's my total initial momentum. They're going to hit each other, collide, and then do something afterwards. So what I want to know is what is going to be the total momentum after the collision. So they're going to hit, let's assume that they bounce. So this is before. After. So afterwards, this 5 kilogram mass is bouncing off to the left. The 4 kilogram mass is bouncing off to the right. And what I want to know is what is the total momentum after the collision? Someone want to take a shot at what the total momentum after the collision is?
It's -9.
Yes. It's -9 units. That's what conservation of momentum is that whatever my total is beforehand, that's my total afterwards. It does not require knowing any more detail. Other than, I am going to throw in one other terminology here, a closed system. So if I take this box and I put it on the table, I'm going to push on it. So I'm going to apply an impulse to the box, so I'm going to give it momentum. And then it stops. So did the total momentum in the box stay the same? I got one.
Yeah.
A yes, and a no? Why are you saying no? I guess you should go
I
first.
guess just because the velocity changed.
Yes. I'm assuming the box did not lose particles as it slid, but it had a velocity that was not 0, and now it has a velocity of 0. So momentum did not stay the same. But I just went into this thing about conservation of momentum. And so this gets into the open system versus closed system. In a closed system, there's no outside influence. In that case right there, when I was concentrating on the box, I was ignoring everything else. The table obviously was interacting with the box. So since if I consider my system to be the box, it's an open system because the table was interfering with it. In a closed system, there's no outside influence. So this is a closed system if these are the only two objects in the universe, or these are the only two objects that are going to interact with each other. There's no planet, there's nothing else interfering whatsoever. And so consequently, open system. Yes, outside influence. So momentum is conserved in a closed system. The initial equals P final. And the sigma here, this capital sigma in front just means sum. I'm adding them all up. Here, what's called the external force, forces that are coming in from the outside times time, is equal to the change in momentum. So friction applied an impulse to the box after I stopped touching it. All right, questions to hear? All right, so that was side vocabulary. So we'll get back to our closed system here. If this if this 5 kilogram mass is going to the left at 1 meter per second, what is the velocity of the 4 kilogram mass? Again, starting situation right here. Afterwards, they balance the 5 kilograms shooting back at 1 meter per second, the 4 kilograms going off to the right at some speed. Well, we can calculate it. Actually, I'm going to, I think I have set up an impossible situation there. So instead of 1 meter per second to the left, I'm going to make this 2 meters per second going to the left. So after the collision, what is the momentum of the 5 kilogram mass after the collision?
10
Is it 10? Close.
Negative 10?
Yeah, that's it. Don't forget, it's going to the left. Direction matters. It's unlike energy, where they don't care about direction. We do care about it here. So negative 10, whatever units. So therefore, I know my total is negative 9. Therefore, what is the momentum, the P final of the 4 kilogram mass? What is the total momentum of this after the collision?
10
No, it won't be 10. Let's think about what we did before. So before, we did 15 plus negative 24 gets you negative 9. And then after, again, that's my total. That's going to be negative 10 plus something.